Okay, you can start. Do you want to first like introduce yourself?
Yeah, sure. Okay, so I can go ahead and get started then. So hi everyone, and I'm glad you were all able to join today. My name is Ilgen Güller. I'm an assistant professor at Penn State. And I've been here since 2015. And today I'm going to present some work on flexible signal phasing and timing plan in a connected environment. So this is work that I actually started when I was a postdoc at ETH Zurich. So I knew Irene back then, actually. And then it's work that I've continued throughout kind of my career here to various different points. And Joyce Liang was my PhD student who kind of did most of the work that I'll be presenting today. And she was co-advised with Dr. Vikash Gaya, who's also in the civil engineering department. So with that being said, I will jump into the talk and I'll try to kind of give you a background first. So I'm sure you're all familiar with traffic signal control and ways of providing traffic signal control. So I'll kind of give you a quick overview of the different types. Fixed time is probably what's most commonly used in the sense that you try to look kind of historically at what happens at an intersection, and then based on your expectations, you provide a fixed signal like fixed green and fixed red duration for each movement. And it could vary from time of day or even for different days, but it doesn't, it's pre-planned. No information is required actively to be able to implement a fixed time. So then the more smart ones that kind of take information in real time and make some adjustments are actuated and adaptive. Actuated, you kind of have a range within which you can have your green times, and so you adjust within that range. And then adaptive can be more robust to larger variations. You might be able to skip some phases sometimes. So all of these kind of basically create a more tailored signal timing than what fixed time might do. The issue is that for both actuated and adaptive, you're typically using inputs from a detector or video cameras, but you're using aggregated traffic information. You're counting like all the vehicles that are there and then trying to adjust your signal timing based on that. So connected vehicles offer some richer information sources because you can get information on individual vehicles. So here I'm going to assume that vehicles provide their actual locations and speeds to a signal controller, and that's within the zone of a signal controller. And that further, sometimes you might be able to actually transfer information from one intersection to another. And another development, which is autonomous vehicles. So in this talk, I'm kind of separating connected from autonomous. I'm assuming vehicles, human-driven vehicles can be connected, but autonomous vehicles I assume are always connected. But they can receive information from the signal controller and they can kind of drive at perhaps different speeds to make sure like you don't stop at a red light. So they can be used to smooth traffic even further. I don't focus too much on autonomous vehicles in this talk, but I will briefly touch on some speed guidance issues as well. So the goal of this work is to develop a signal control algorithm. One of the major things that I deal with is looking at less than 100 penetration ratio, meaning we have still some traditional vehicles that look like what we drive today out there in and just driving. So I'm not relying on I have this technology and every car on the roadway has this technology. Now I'm just assuming, okay, there are some cars that have these connectivity capabilities, maybe some that have this autonomous capabilities, but not all have it. And then the goal is to leverage CV information. And then I'll show how I did do this. We try to infer information on non-connected vehicles as well. we try to provide very flexible phasing options. So we don't really rely on a traditional phasing scheme like a dual ring scheme or something, if you've heard of that before. We think that the signal timing could be very flexible once you get information from connected vehicles and kind of change how you perhaps implement your signal timing. So I'm going to, again, briefly talk about how we can provide speed guidance. And when I do that, I'm going to talk about autonomous vehicles, but also providing speed guidance to human-driven vehicles. Multimodal traffic, I'm not going to touch much on in this talk, but we can incorporate buses and pedestrians and other modes into the algorithm. And I'm going to, again, at the very end, touch on how you might extend this to provide signal coordination along arterials. But before I get into any of those more complicated ones, I wanted to introduce the algorithm at a very, very simple intersection. And this is kind of a toy intersection in the sense that this is not kind of what the end result will be shown for, but this is the intersection that I use to introduce the algorithm. And so in this intersection type, we have two one-lane roads. And the one road travels from south to north, one goes from west to east, and we're trying to figure out the signal timing at this intersection. So let's say these rectangles represent the cars on the roadway. We have some CAVs that are shaded, some that are non-CAVs, they don't connect to the intersection, they do not communicate with the intersection, that are shown by these hollow boxes. And then we assume that these connected vehicles at regular intervals, and this could be like every 10 seconds, they tell the signal controller their location. So they tell them, for example, I am X meters from the intersection, and they tell them their speed. My current speed is, for this one, it's 0. For these ones, perhaps it's greater than 0. So then the algorithm takes this, and first it tries to identify, can I infer if there are any other vehicles on the roadway that are not connected? And it does so by considering stopped vehicles. So if it sees a stopped connected vehicle, based on its distance from the intersection, it makes assumptions about whether or not there might be other cars in front of it. So if that car is stopped far from the intersection, it assumes, well, why would that car stop so far from the intersection? There must be another vehicle in front of it. So that's kind of how, based on how far a stopped connected vehicle is, it assumes that, okay, there must be this many non-connected vehicles in front of it. So that's kind of how we bring in the non-connected vehicles into the algorithm. But then, of course, in this way, you miss other vehicles. Like this one here, it's stuck in between two moving connected vehicles, so you don't see it. Similarly here, you don't necessarily know this one's presence. So at the end of the day, the input to your algorithm from what you're getting from the connected vehicles becomes something that looks like on the right-hand side. You have your connected vehicles, and you have assumed non-traditional vehicles. So then the next thing that we do is, our goal again is to try to come up with a signal timing plan that will minimize delays. And in order to minimize delays, we can consider what is the best sequence of departure for cars so that they experience a minimum delay. However, once you start getting into individual cars, one, you start running into a lot of computational issues. Two, you might start running into issues with switching of signal too frequently. So rather than looking at, okay, what sequence should individual cars discharge at, we look at what sequence should platoons of cars discharge at. And here, when I'm talking about platoons, I don't talk about necessarily cars platooning or following each other at like a low headway, but I'm talking about based on how cars are traveling, can I consider them as a platoon? So we assume that stopped vehicles, for example, stopped vehicles, these ones shown in the red, are a platoon, and then driving vehicles could be platoons if their headways are smaller than a certain threshold. So the moving vehicles can be broken up into multiple different platoons based on their headways. So now I had this input to the algorithm, that was the middle figure. Now I'm actually changing that slightly and making these platoons of cars my unit of consideration in the signal timing algorithm. So I'll kind of show you a quick video on identification of vehicles, and I'll pause it actually. Identification of traditional vehicles and platooning. So in this simulation, you'll see that we have yellow cars that are conventional or non-connected vehicles. We have light blue cars that are connected but not autonomous. In this one, I'm not going to have any autonomous vehicles. So, and then the rectangles are not platoons and the ovals are platoons. So you can see all of these cars on the left-hand side. By the way, are you seeing my mouse? Okay. All these ones on the left-hand side are in a platoon right now. And you'll see that this yellow car, it's conventional, it's not being seen by the signal controller, it's not being platooned, but as soon as this blue car stops behind it, they turn oval, meaning they're both seen by the signal and they were platooned with the conventional cars behind them. So again, this yellow car, these are all going to turn an oval, meaning they became a platoon. So kind of, you can see how the algorithm updates as it gets more information from the cars and especially connected vehicles stopping. So then the whole idea is I have this input, different platoons, say I have these 4 platoons, that's an input to my algorithm. I'm trying to come up with the best signal timing to be able to minimize delay. So rather than looking at potential different signal timing options, what I do here first is I look at potential different discharge options. So I say, okay, if I have these 2 platoons, well, either I'm going to give green to the east direction first, or I'm going to give green to the north direction, P1, P2. If I give green to P1, then, well, I could continue that green to let P3 discharge, or I could switch the signal to let P2 discharge, and vice versa. So I kind of enumerate through all possible combinations. And so I have different sequences, P1, P3, P2, P4. P1, P2, P3, P4. So I have all these different possible sequences of departures. And then I calculate the delay for individual vehicles based on these departure sequences. So I say, okay, P1, I see 2 vehicles. I think there are 2 vehicles in that platoon. If I give green to this, when do I expect the first vehicle to discharge? When do I expect the second vehicle to discharge? Based on that, I say, okay, I assume this platoon is going to have this much delay. Then I do the same thing for P3. How much delay do I expect them to have? And so based on the sequence that I'm looking at, I try to figure out, okay, what time do I expect it to depart? What does that mean in terms of delay? And I'm trying to minimize either my combined departure time, which is the same thing as minimizing my delay. So I pick a sequence which I think is going to minimize my delay. And then based on that sequence, I convert that to a signal timing. P2 has to go first, so it's going to get green first. P1, P3 is going to get the green next, so I'm going to switch. And then P4 is going to get the green next, so I'm going to switch again. So my final signal timing plan perhaps looks something like this. And the duration of those greens, again, I determine based on when I expect this last vehicle that I see in the platoon to depart, and then how much kind of a gap do I need, like a yellow time or a red time, and then I switch to this other approach. So I determine the length of the green time based on my estimations of when I expect the last vehicle in that platoon to depart. You can see that if there are vehicles that I'm not seeing here, for example, for P4, if there is a vehicle right behind this, which would have logically made sense to let this charge, but it doesn't, then I'm going to kind of be off in my estimations. So you can imagine that the more information I have, the better I'm going to be at predicting these and tailoring the signal timings to the actual traffic. Any questions so far? I'll take a pause.
I have a question. So what would happen if you have a vehicle just that you don't see just behind a connected vehicle? Like, would
Like
it
right there?
be able to stop on time if you're cutting the signal at that point? Because you know.
Yes. Yeah, so we do incorporate some yellow time like a traditional signal would have. So I mean, it would be up to that car whether it chooses to try to stop or whether it chooses to try to go. So it could kind of go either way, but the cutoff would be in more like a traditional setting. It wouldn't just abruptly change.
Okay, thank you.
I have another question. You said that the Pluton is formed when the first connected vehicle arrives. What if we have several like normal vehicles waiting and no connected vehicles go there?
Yeah, so that's a great question. So there is issues with not seeing traditional vehicles. So in that scenario, those traditional vehicles would wait a really long time. And actually, I'm going to show towards the middle of the presentation where we look at equity of delay. And I'm going to look at the distribution of delay for all vehicles. And I'm going to show how we might be able to reduce the maximum delay in the system so that we're kind of trying to accommodate for these scenarios where we might not be seeing some vehicles. But definitely, that's probably one of the biggest concerns with a connected vehicle-based algorithm. We do have max outs. So I mean, at the end of the day, you do have like a max out. We do max out at some points, but it's not like a short max out.
Okay. You can talk or type your questions if you have any.
I will respond to Yoonghun, I think. I'll respond to your question in a little bit. I'll show some figures. So I will keep moving on. And then if you have any other questions, feel free to interrupt me or, just write it in the chat. So this is comparing the algorithm to a fixed time control. And I forgot to start this one. So the left-hand side is a fixed time, right-hand side is a flexible connected vehicle algorithm. The arrival pattern of cars is the same. The fixed time control is timed in a way that should be good for the demand that we observe. So it's not just a random timing, but you can still see that the connected vehicle algorithm does better, especially because it can tailor to the changes in demand in a more rapid form as compared to the fixed time that is static, doesn't really respond if more vehicles are coming from one direction versus not. So you can kind of see the queues getting larger on the left-hand side as compared to the right-hand side in general. So with that, this is giving me issues moving on. Okay, so then as I mentioned, we can determine this optimal sequence by enumerating all options. And here I'm making a switch in the algorithm briefly, because now I am moving on to a more complicated intersection where we have two directional traffic and we have left turning movements. So when we move into the more complicated the intersection type, actually what ends up happening is that we increase our possible phase options. So before we only had kind of these yellow and this blue, you could kind of alternate between those two. So now we assume that it is possible, for example, to implement both a through and left turn phase and a left turn only phase, for example, for the north and south. So depending on the volume of traffic that we have, in order to serve that left turn, northbound left turn, for example, we might choose to go with this purple phasing or with this green phasing, depending on kind of where there is more demand. So when we switch to this kind of a more complicated intersection, it becomes really complicated to enumerate different platoons, because the platoons can change. Before you actually implement the signal timing, you don't know if these left turn vehicles should kind of be grouped together with the through cars, or if they should be grouped together with the opposing left turning cars for the algorithm's sake. So rather than enumerating platoons, we switched to enumerating different phasing options. And then the way it works is that you enumerate different sequences of phases. So at each point you assume like you go with yellow first. And then once you go with yellow, you can go with any other phase again. So it's kind of enumerating all options. And then you assign cars to these phases if they're there. So you look at, okay, yellow is first, which cars are there that could fit into the yellow? And do they form a platoon? So whatever cars form a platoon that could be served in this yellow phase, go into that group. So those get eliminated from your group of vehicles that you see. Then you look at, okay, what's next? Maybe this one is next. So you platoon those vehicles, assume those go there. So in this case, you could have multiple of the same signal back to back. That would mean, for example, if we had 2 yellows back to back, maybe we have the first one gets filled with the stopped cars platoon, and then the next one gets filled with the moving cars platoon. So you kind of fill in as you go. And if there's no cars remaining that you can fill in for that gets a penalty. You assume that phase is going to give you a lot of delay so that you kind of eliminate empty phases from your signal phasing option. And so when you do that, you can now imagine, once I start enumerating all these phases at each level, I have 8 options, the computational time goes up rather rapidly. So here is a figure showing how that might change the computation time versus your vehicle delay. So in this figure, I assume that we evaluate, for example, when I say 3 platoons enumerated, that means I put 3 signal phases. So for the first 3 layers are enumerated, the first 3 rows, and then after that, I append a fixed sequence. If I do 4, I'm enumerating the first 4 options and I'm appending a fixed sequence. So the larger the number of platoons I enumerate, the better I'm doing at reducing the delay. The orange line shows that, which is expected because I'm making a better decision. But you can see this blue line, which is the computation time or the time for control action, goes up rather rapidly. Once I'm at this point, the 6 platoons enumerated, my computation time is already 4.5 seconds, which is not going to work well for a real-time application. So then this is where we start considering different solution methods rather than enumeration. The first one that we considered was, well, what if we don't enumerate all possible platoons at each level, but only a fixed number of platoons? So let's say we picked 3. And we decided to prioritize platoons with larger number of vehicles. So we assign cars to each of these phases and we look at which one has the most number of cars. And we say, okay, the top 3 with the most number of cars go and gets into our sequence. We ignore the other ones as options. And we actually tried different criteria and we found that the larger number of vehicles worked the best. We kind of did like predicted delay of that platoon. We looked at kind of how far the last car might be from the intersection. So we tried a bunch of different criteria and it ended up that the larger number of vehicles worked the best for this intelligent tree search. So at each level, we now trim our tree so that it becomes much easier to enumerate. And then the second is we tried heuristic algorithms, mainly genetic algorithms, and where we created different chromosomes made up of different sequences of phases. And then we assumed each of them, we calculated the delay for each sequence, assumed that was a fitness score and kind of evolved the genetic algorithm like that. The problem with the genetic algorithm is that we found that a lot of benefits when we kind of get an optimum signal timing, we found that the first few sequences mattered a little bit more than maybe the remaining sequences. So you could gain a lot of benefits by setting the first 2, 3, 4 phases correct. And the benefits kind of started to decrease after that point. So when you did genetic algorithm, you kind of lost that information in this crossover and mutation process. You didn't retain information from the beginning of a phase. And so it kind of got messed up. Whatever benefits you were observing from a parent, once you did the crossover mutation to create new genes, you kind of lost that information from the parent gene. So we came up with 2 modifications. One of them was a sequential genetic algorithm where we fixed the first gene of the best solutions after a certain number of generations, and then kept those and only changed the remaining ones in the genetic algorithm for a number of generations, and then fixed the first two of the best and kept doing the same thing. So we kind of fixed those initial phases to retain that information as we move forward. And then the second one was where we did a voting recombination. This is basically, we said, okay, maybe if the same gene is appearing or the same phase is appearing in the same sequence in multiple good solutions, maybe there is some benefit to having that sequence, that phase in that sequence. So we kept that when we were generating new solutions. But if it was kind of random, like this row, it's all different, then we said, okay, we'll just create a new one for that randomly. So we kind of fixed a few of them that appeared at the same spot and then randomly generated the other ones. So here is the result. So this kind of goes back a little bit to the question that was asked, because on the x-axis, we have the penetration ratio of CVs. And you can see that as there are more connected vehicles in your traffic stream, of course, this behaves better. And if you compare this to an adaptive signal, an adaptive signal typically lies somewhere around here. So once you go above that 40%, 50% mark, the connected vehicle algorithm starts doing better. And it's not on this figure, but we've looked at that before. So you can see that more connected vehicles, there's still benefits, but the benefits start to decrease after 60% mostly. But there are large gains in delay as you go up to about 60% connected vehicle penetration ratios. And then you can see that the different algorithms that we suggested, complete enumeration, we assume this red dashed line is the ground truth. We're evaluating all possible solutions. The intelligent tree search, where we eliminated a part of the tree, performed really well, almost the same as complete enumeration. So that was very promising. The genetic algorithms, not so well, but not horrible either. This, for example, the sequential genetic algorithm, this gray line, does a fairly good job of kind of mimicking what happens in the actual signal timing. Then we move on to the right-hand side, which is the computational effort. So as I mentioned, complete enumeration, the computational effort grows very rapidly. And this is the log time. So you can imagine this is more than linear growth because it's growing in the log time. The problem with intelligent tree search was that even though the computation time was much lower, its growth rate was again exponential. So if we wanted to increase further the number of vehicles, the number of intersections, we thought we would run into problems with computation time with the intelligent tree search algorithm as well. But you can see that the genetic algorithms are rather flat in terms of computation time. So you can actually scale those fairly well without increasing computation time. So we proceeded with the sequential genetic algorithm for the larger intersection solutions. Any questions up to there? So then I will briefly touch on speed guidance. We looked at how do we provide speed guidance to vehicles. And as I mentioned, we thought we can provide speed guidance to human-driven vehicles and autonomous vehicles. So our connected vehicles, we assumed some were autonomous, some were human-driven. And out of those human-driven connected vehicles, we assumed some of them could receive speed guidance while others did not. And the speed guidance was basically, we figured out what speed cars had to go to get to the intersection at their expected departure time that we calculated. So if that was, for example, the first car that was going to discharge, it was exactly when we thought the green would start, but for other cars, we always had an expected departure time calculation. So we could provide each car a speed so that they would arrive to the intersection at the time we expected them to depart from the intersection. And for autonomous and human-driven vehicles, it was very similar to speed guidance process, except that when we provided the speed to the human-driven vehicles, we assumed humans would have a time to react to the information that was given to them, whereas we assumed the autonomous vehicles would not have that reaction time and would react instantly. So the two types of vehicles, even though we aimed to get them to the intersection at the same time, they received a different speed guidance, which we thought would be the best for that type of vehicle. I will skip this one. So one more thing we did was we checked, okay, how well can human-driven vehicles perform compared to autonomous vehicles? Meaning we assumed, let's say we calculated a design speed of this equivalent to this blue line for a human-driven vehicle. We assume that an autonomous vehicle can drive that speed. We're going to assume that autonomous vehicle does a pretty good job of adopting that speed and driving that speed. On the other hand, a human is likely not to adopt that speed. So if somebody tells me to go, okay, you need to travel at 10 miles per hour, I might be like, no way, that's way too slow. I'm gonna go at 13. So I'll adopt a different speed, likely, right? I'm probably not going to adopt exactly 10, which is what the system is telling me. Or I might adopt something slower. And then once I adopt that speed, say I was told 10 miles per hour, I adopted 13. Well, I'm trying to drive 13, but I'm really not good at it. I'm kind of going to 12, going up to 14. I'm kind of in that zone, but I'm fluctuating. So the green is what I'm actually driving. The blue is what I expected as the algorithm that the human-driven vehicle would drive. So we tried to understand, okay, how would that make things really worse? Like, would that make speed guidance basically ineffective? The fact that I tell the person to drive at blue, but they go at the green. So then we looked, and it looked like it would make things worse, of course, compared to autonomous vehicles, but there is still benefits to providing speed guidance to human-driven vehicles. So these are 3 time space diagrams of the same vehicle arrivals. So at this location -100, each car comes at the same time, and the red and the green shown are exactly the same. The difference being at the top one, there's no speed guidance. Here we have autonomous vehicles that receive speed guidance in the middle, and at the bottom we have human-driven vehicles that receive speed guidance. So you can see that once autonomous vehicles start receiving speed guidance, some of these stopping movements that are observed here get eliminated. So these pink lines are a lot smoother than these blue lines that you see here. Similarly, when human-driven vehicles get speed guidance, it looks better than this top one, but doesn't look as good as this middle one. So like there's this one car here that if you looked here when it was autonomous, it kind of didn't stop at all, but it kind of stops when it's a human-driven vehicle, which affects the cars following it. But on the right-hand side, things look a lot better, a lot smoother. There's a lot less stopping maneuvers. So human-driven vehicles receiving speed guidance could improve things. And so if we look at kind of what that would mean in terms of delay and number of stops, left-hand figure shows delays, right-hand figure shows number of stops. The different lines are different percentages of connected vehicles. So as we go further down, that means there's more connected vehicles and delays are lower as expected. And as we go right on the x-axis, that's the fraction of human-driven vehicles receiving speed guidance. So for example, this 100% means that 100% of connected vehicles receive speed guidance. And if you look at this, you can see that the speed guidance doesn't have an impact on delay, which is completely expected on our end because we didn't design speed guidance to change delays. We tried to get them to the intersection at the time that we wanted them to. So we weren't changing the signal timing, we weren't expecting it to change delays. We were just doing this to reduce stops, which you can see on the right-hand side. As you have more cars receiving speed guidance, the lower the delays become, especially if the connected ratio is larger. So you can see that with no connected vehicles, no speed guidance, the average number of stops is about 0.75, whereas it can go all the way down to 0.3 once you have 100% connectivity and 100% speed guidance. But you can see that even without speed guidance, just the algorithm on its by itself, the signal control algorithm, reduces some delay as well. Any questions about those results? Okay. And this is when you have 20% autonomous vehicles, the results look somewhat similar. So this is going back to Negin's question about, what happens to the cars that are waiting. So we said, okay, well, we have this algorithm, great, but is it really equitable? Does it make sense? Like, does it prioritize certain vehicles over other ones? So we looked at the delay distribution histogram. The delay distribution histogram is the number of vehicles that experience a certain amount of delay. And if we zoom in on the right-hand side here, you see that even though most vehicles have delays less than 50 seconds, for example, there's a lot of vehicles that have really large delays, over 150, 200 seconds. So here we're talking like on the order of minutes now, cars getting delayed. So then we said, okay, well, that's not good, right? So a lot of vehicles are benefiting, but there are these vehicles that are really suffering. So then we modified our algorithm and basically implemented a threshold. We said, okay, when you're doing your evaluation of different sequences, eliminate those that would result in a maximum delay to a vehicle greater than a certain amount. So the threshold is that maximum delay that is allowed. So we tried different maximum thresholds, threshold 150 seconds, 130 seconds, and this figure on the left-hand side plots for different thresholds what is the actual maximum delay that you observe versus the average delay. The first thing to notice is that as you implement lower thresholds, 150, 130, 110, the average delay is barely changing in the beginning. So that means I can actually kind of do the same thing by just readjusting my signal timing slightly to eliminate those really large delays. And then you can see that I can actually push this threshold even further down, and I can actually do pretty good. I can get to one that has a maximum 70-second delay with a relatively, a little bit slightly higher average delay, but still, not that much higher than the 19.5 that I was seeing before. But after a while, of course, if you keep pushing the threshold to be lower and lower, now I'm starting to get larger average delays, and I actually can't even meet my threshold at some point. It's just not feasible. We don't have any feasible solutions. And so we kind of looked at what that meant in terms of equity of delay distribution or inequity of delay distribution. So this is kind of the Gini coefficient, if you've heard of the Gini coefficient. It shows the vehicle number and the cumulative delay or percentage of cars. So if you were on the diagonal, that would be the ideal scenario where each car has the exact same kind of contribution to delay. The further you are towards this threshold, that means some cars are contributing really much to the delay, whereas other ones are not at all. And so we could see that with the threshold, this line got closer to the diagonal, meaning we were able to make the system a little bit more equitable. Two more things I'll talk about and then I'll be done. We did incorporate pedestrians into this algorithm. So in order to incorporate pedestrians, we basically did something very similar, but we just added more pedestrian phases. Sorry. And I exited. Okay. I am coming back in. Sorry, that was my fault. Okay, share. Okay. Are we all back? Okay. So we took the same phases and then added the same phase with a pedestrian crossing option. The pedestrian crossing option basically set a minimum duration to that phase to allow for pedestrians to cross. So this phase could be very short to just allow cars to cross, whereas this phase had to be a little bit longer to allow pedestrians to cross. And so we did the same thing. We enumerated the results and tried to come up with the best possible solution. And the end results looked like this. So we tried different pedestrian delay weights, meaning when we calculated our total delay in the algorithm, how did we weigh pedestrian delay to car delay? So you can see the more pedestrian delay weights I have, the smaller the pedestrian delay becomes. That's the blue line. The more pedestrian delay I have, the larger the vehicle delay becomes. That's the red line. And these green and the purple ones are person delay and average weighted delay. And you can see there's a sweet spot there to balance between car and pedestrian delay. And then we extended this to arterials. So we tested it on a three signalized arterials back to back. We tried different scenarios. We tried a decentralized algorithm where each signal operates independently. We tried a centralized algorithm where the three intersections make their decisions simultaneously. And we actually find that the decentralized algorithm worked better, which was a little surprising. But we found that in order to make it better, we had to make sure that they were sharing information, meaning once a vehicle left one intersection, it automatically got included in the information of the next intersection. And we were able to do better than a SCATS in terms of average person delay. So this yellow line shows the person delay of our algorithm, and this dashed line shows the SCATS algorithm, what the average person delay is. I will stop there and thank you for your attention. And if you have any questions, I'm happy to answer them further now.
Thank you very much. It was a really interesting topic and it was a great talk.
Thank you. Any questions?
I have a curiosity question. Sure. So what was the headway that you considered for the cars to be a platoon?
The headway threshold, I believe, was 2.5 seconds.
2.5 seconds. Okay.
Yeah, we actually did a grid search for different combinations of headways and spacing. So, considering different combinations, and we plotted the computation time versus the average delay. And we picked one where the average delay was very similar to considering them individually, but the computation time was significantly lower. So we actually had like a grid search that we did to come up with that conclusion.
So it's basically chosen for your own algorithm. It's not something that you decided based on other data, right?
This was chosen for our algorithm, correct. And I don't know if it would apply to other things. That's a good question. I'm not sure if it would be applicable to other questions or other scenarios.
Okay, interesting. Thank you.
Sure.
And did you consider all the vehicles to be normal vehicles? I mean, no truck or bus or those things?
So I have incorporated buses into this algorithm. I didn't show any results from there, but I have the same algorithm, but assuming all buses are connected. And trying to account for bus stops, for example, if you know there's a bus stopped at a stop, how does that impact how you implement your signal timing? I have not considered trucks. That's actually the next step, incorporating trucks, because of course trucks behave differently than cars, and so they would definitely impact the results of the algorithm and how you should go about it. So that's actually the next step that is going to come in this, trying to account for different types of vehicles, different acceleration profiles, different lengths, etc. Any other questions? And Irene, going back to your question, I pulled up the paper. So this is the grid search I was talking about. The left-hand side is showing the computation time, then the average delay and the average number of stops. And so we picked a value that was, I believe, somewhere right in here, 2.5 to 15 or something like that. So you can see that 2.5 to 15 falls in the lowest average delay category, the lowest number of stops category, but also in the lower computation time category. So that's kind of where those numbers came from for our work at least.
Okay, interesting. Yeah. Thank you.
Sure.
If there isn't any question, we can end the seminar here.
Okay, well, thank you very much for having me.
Yeah, we appreciate that you put so much time and gave us this great talk.
Thank you.
Thank you.
Enjoy your break.
Yeah.
Thank you.
Bye-bye.